All right, so the final topic I guess we have to talk about in site investigation is using indirect methods. And I guess we've made the point before that indirect methods is code, I suppose. It's a euphemism for geophysics. And geophysics comes in two varieties. It comes in the form of surface geophysics, which are what these first four methods are. You do something on the surface, you stand on the ground surface and measure something. And typically that measurement is a proxy for what's in the subsurface. So in geomagnetic methods, you would measure how the Earth's magnetic field that drives a compass is modified ever so slightly by pieces of iron below you, not just metal but iron. In geoelectric methods, either direct current, alternating current, or electromagnetic methods, we measure the electrical properties or the electromagnetic properties of the subsurface and how they vary in space, laterally, and in depth, and use those contrasts and changing properties as a proxy, if you like, for different materials, sands, clays, gravels, rocks, by trying to correlate those with known values. And seismic methods, we use the acoustic impedance, which is the product of density and, most significantly, the seismic velocity, the same speed of sound in rocks rather than the speed of sound in air, with which we're communicating now. And in gravity methods, it measures the change in the gravitational traction of the Earth by things like voids. So if you're standing on top of a big tunnel, then you can sometimes sense the change in gravity, not yourself, but by using very accurate methods of doing that. So those are all things that are prosecuted, if you like, from the surface. And well logging are the same kinds of geological measurements, but are done in the boreholes that you might have drilled in the things we've talked about in the past. So that's really what we're talking about. We've looked at this kind of figure before to make the point that the difference between these methods is that direct methods will typically be a one-dimensional borehole. They could be a two-dimensional trench, which you'd bring a backhoe on site to be able to look at the subsurface. And of course, if you excavated the whole site in 3D, you wouldn't have a site to deal with. So that's not quite so practical. So what geophysics does is allows you to fill in the big picture in 3D. So the advantage is that you can cover large volumes and large areas or lengths quite straightforwardly from the surface, but the information you get is really indirect. It's a proxy or an inference of what's down there. And so measurements of how electrical conductivity or resistivity change with depth is only a proxy for what the material properties are that you'd like. And it's not the stratigraphy that you want to know about, sands versus clays. It's actually the hydraulic properties you probably want to know about, capillary entry pressures, permeabilities, porosities, etc. And so those are really only inferred by using geophysics. And so typically the way that it's used in these different workflows is that you, and actually this isn't a bad figure to illustrate it, is you have a drill hole somewhere that sits, so this is a plume on the edge of a lake, and at the edge of the plume you have a drill hole, and from that drill hole you have a core. So this is, you could calculate exactly what the volume ratio of this core is relative to your site. Probably not very much, probably a millionth, something like that. But what you do is that on these places where you have drill holes, you have very accurate information and samples that really tell you what exactly is there and has some physical meaning to what you might want to know. Permeabilities, porosities, entry pressures. And so what you'd use geophysics for would be that between two boreholes, you could run a geophysical survey line to fill in what the stratigraphy looked like between them. You know exactly what it is where it hits the boreholes, and it tells you, infers what the fill-in characteristics are over the rest of your site. And so that's really what we're attempting to do. And so the idea is that geophysics is less precise in terms of defining exactly what is there, but it allows you to be able to join the dots, I suppose. And so we'll emphasize the ones that are used in environmental remediation or environmental geophysical surveys and to understand remediation. Has anyone taken or is anyone taking the Geosciences Environmental Geophysics class, which runs now? Not a Soul, by Andy Nyberg. It's actually an interesting class. You go out and you use a few of these methods: seismic, electrical, I would guess, GPR, ground penetrating radar. And in the past, they've done it over a disused land, a small landfill over at Toft Trees, and they've tried to characterize it, etc., and write a report at the end of it. So, interesting. So, never mind. So, we'll talk about these different proxies. So, Geomagnetic Methods, as the name suggests, tries to measure a change in the magnetic field of the Earth. And so, as you know, maybe there's a picture here. I think there is a picture here. If you look at what the core does at the center of the Earth by fluids roving around in this liquid iron-rich core, it sets up a magnetic field which comes out at the poles, and the lines of direction of this magnetic field, the reasons why you have an aurora, right, is you have the magnetic field at the pores interact at the poles interacting with plasma that comes from the sun, I believe. And so they exist around the poles when they happen. Borealis in the north and Australis in the south. And so these lines of action of the magnetic field have a certain inclination where they come to interact with the surface of the Earth. And I guess around where we are, the inclination of them is at 70 degrees to the surface of the Earth. This is the ground surface. And so where these come through, you could imagine that where you have something that's magnetic that would attract these lines together, then they're more strongly bunched. And so if these are lines of equal potential, if you are able to run a section by taking an instrument that you physically place at a variety of different locations and take a measurement at each of those locations of what the strength of the magnetic field is, and its orientation may be, then if these lines of force are bunched up to go through these 55-gallon drums which are existing below the surface, then you'd see a change in the strength of the field as you go across here. And I think that's exactly what this is showing here, that if you go across this array of targets that are different from the material around it, are iron targets, if you're very close to them on the surface, you might be able to measure changes in this field which are really quite detailed and might pick out the locations of individual features which would be represented in this magnetic field. If you go higher than just above the ground, half a meter, 2 meters, and 4 meters, then the signal gets progressively more diffuse. And so if something is present relatively shallow depth, then you have the potential to be able to pick it up merely by making measurements on a section that goes across here. And those are measurements of the strength of the Earth's magnetic field at very, very fine resolution. And so just from here, I don't know about this. I've never used, actually I have used magnetic measurements. But you can pick up a drum that's buried by 10-foot depth, etc. And so that's the mechanism. And so you don't need to know much about it to be able to use it. It's really only useful if the targets are magnetic. It won't find holes. It won't find other things in the subsurface. So if you think that the contamination has come from something like that, then it's a decent mechanism to do it. The other thing, it is quantitative as well, not just qualitative in that you can find things, in that you could invert for the signal that you get by going across the surface to be able to figure out exactly what the feature is that's in the subsurface. And the inversion for a target which exists at some depth below is that because the inclination of this magnetic field as it comes across, the distance between the trough, first of all, the signal's asymmetric because of the fact that this is not coming in directly. It's because this is the northern hemisphere, I guess, so it's coming across here. And this would be wherever we are, at 40 degrees north. I'm not sure exactly what our latitude is. But if you measure, it's asymmetric first of all because of this, but also if you measure the distance between the peak and the trough and get this length, then the depth of this target is approximately half of that separation below the surface. So it's kind of interesting. So I'm not sure. I think our aim here in this class is to at least alert you to what the techniques are. You might use them at some stage, or more likely you might think about hiring someone to use them for a site you're working on, because you know they can work. So the technology is there. It's relatively straightforward technology. It comes in two flavors, I'd say, and either as permanent magnet magnetometers, which are ones that measure to high resolution, 1 nanotesla, I guess 10 to the minus 9 teslas, which is the measurement of the strength of magnetic field. And typically those are instruments the size of a theodolite or a transit that you place on the ground. You accurately level them, you walk away from it, and it takes a reading of exactly what the field strength is at the ground. You move it 10 feet or 20 feet or 100 feet and repeat to get the reading as it is. And the other kind, which are proton magnetometers, which work in a similar way, I think, but are much less accurate. And I guess I didn't search these up, but let's do that. I bet you we can find a picture of one, maybe. We'll come back to that in a minute. Good news on Iran in the background, you see. Let's see if they have them. Yeah, okay. Which is this? Wouldn't you love to walk around a field with your friends watching wearing this? Yeah, proton magnetometer. Oh, it's in China, in Shenzhen, the free trade zone. So I don't know exactly. So, I mean, the basic idea is that these are the sensors. I always think of these not as arranged like this, but usually it's a long pole, almost like walking a tightrope, maybe 6 feet wide, that has whatever instrumentation in it, and you just physically walk across a field, and it takes a profile of exactly what the magnetic field changes are as you go along and across the other side. Don't know if there are others, ones that look more like the ones that I'm used to seeing. Yeah, they're just an antenna. So you walk across the field with some form of antenna. You don't have to stop. It just measures it continuously, not as at high resolution as if you use a regular magnetometer, which is just a box that you put on the ground, which I would suspect that this might be a more accurate one that does a reading at a particular location. This looks like it might do it by pushing a probe into the ground, and allows you to, or here's an even better one. You wear it on a backpack with GPS attached to it, apparently in the middle of Monument Valley, which I guess is that, right? It doesn't seem like a normal place that you want to use it, perhaps. But anyway, so those are magnetometers. We'll come back to that. And so that's the idea. So all you physically want to get out of this is a profile that would look something like the profile we had on the previous page. So one of the final slides we'll talk about is what you would use all of these different methods for, what situations, when they work, when they don't work, and so we'll summarize that in due course. So, measuring the magnetic field of the Earth. Geoelectric methods don't measure the electric field of the Earth, but they do measure the electrical properties, the DC, direct current electrical properties of rocks. And so in other words, if you take a sample, and you know that if you take a resistor from a radio and you measure the resistivity of that in ohms, you get a certain value for that component, which is its resistance in ohms. But if you take a sample of rock, you can measure a property of that rock, which is its resistivity, which is its resistance basically per unit volume, I guess, of the system. And so geoelectric methods measure the change in resistance, or its inverse, electrical conductivity of rocks, and try and use those to be able to infer what the structure in the subsurface is. And they are completed in one of two ways. And I'm trying to see which one of these figures denotes which, because they look kind of similar to me. And they would be in profiling and sounding. I guess, yeah, okay, I can barely see this. So here's the idea in profiling, and this is sounding. So they're intrinsically different. So profiling means that what you could do, well, let's go a little further. So we'll talk in overview about this. So this is the basic idea, is that you take two electrodes, two pieces of rebar. You put these pieces of rebar into the soil at points A and B, and you attach them to a battery. And as a result of attaching them to the battery, current will flow from A to B, and it will flow on a variety of different paths. These are the paths that the actual electrons would take. And in the same way as groundwater flow, if you have a high head here and a low head here, then these would be the flow paths of the water molecules. And perpendicular to these flow paths are, what are these? You know, you must know. What are the lines at 90 degrees to flow paths, flow lines? From, must have done it's 452. No? Equipotential, right? So they'd have equal heads. So anywhere along here, if you had a, whoops, sorry. I don't know if you've, well, maybe you've done, maybe in 303 we had a question like this. If you have water on one side of a sheet pile wall, water on another side of a sheet pile wall, then the flow lines that link this would be something like this, high to low potential, and the equipotentials would look something like this. Do you use flow? Did you draw flow nets, by the way, in 432? Yeah. So each of these lines here would be flow lines. This would be the pathway that particles of water would go. This would be an equipotential given by this measurement of the head here. It would, I guess, just be equal to this elevation here. This equipotential here would have the elevation of this head here, and these would be equal drops in potential. So these are the same. So in the same way that electricity is a potential flow, this would be, say you put 100 volts across this by a battery between these 2 points. It would make electrons flow along these paths. And if this was 100 volts here, this is 0 volts here. I don't know how many of these are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's make this 120 volts. Then this would be 110, 100, 90, 80, 70. Oh, sorry, I did it wrong. Did I do it right? These are the equipotentials. Sorry, these are the flow lines. So this is 1, 2, 3, 4, 5, 6. Yeah, it is 120 because it's symmetric. That means it's 12. So this would be 120, 110, 100, 90, 80, 70, 60, 50, etc. And so what would happen then if you now took two other electrodes with a ohm meter or a voltmeter on them, just like you could buy in Radio Shack before they went bankrupt, put it into the ground, and you'd measure a difference in voltage here, which would be 120, 110, 100. This would be 90, 80, 70, 60, 50, something. So you'd measure 90 here, and if it's symmetric about this, I guess you would measure 30 here. And so you'd get a measurement of the potential drop across here. And so what you could do is you could put them at points M and N, but you could also stretch them out to be able to map the whole distribution of voltage drop as you go across this top part of this segment. And then you could use that in some way. And so if for some reason there was, so you could use this measurement here of the voltage to be able to say something about what the electrical conductivity was of the material underneath, basically. And you can imagine that as you take these electrodes A and B further and further out, then they penetrate deeper and deeper in making this kind of flow path. And so you potentially sample deeper and deeper as you both move A and B out but also move M and N out further as well. You sample a bigger piece of the earth beneath. And so the bottom line is, by putting electricity into the ground and by measuring it in the central location, you can say something about what this distribution of the flow field looks like. And from these measurements, you could say something about the electrical conductivity of the subsurface, which you want to be able to then link to something about its geological characteristics, I guess. And so coming back to this, you can do this in two modes. You can do it in terms of profiling. And so profiling would be that you would take this arrangement with electricity in and measuring the voltage drop in the center as a template, and you'd physically move it from one place by uprooting it and physically moving it down the line. And I think I have a picture of that which shows this. So in other words, you'd have this template placed here. It would have the electricity going into the ground on the outside at A and B. You'd measure the voltage drop in the interior at M and N, and you'd get one measurement. You'd pull up all these stakes, you'd physically move it to another location, and then you'd do the measurement here. And then you do the measurement here, then you do the measurement here. And so what this would tell you is, if this is able to tell you something about the electrical conductivity in this particular place, or resistivity, it would tell you how, as you went from one location to another, how that electrical resistivity might change. And you'd be able to pick up this bed without drilling, without looking at anywhere in the subsurface, but you'd be able to pick this up. So that's one way of doing it, which we'd call profiling. So we've called this profiling. So it's basically a traverse. So as you go across here, if you could measure the resistivity, this is resistivity. And it's saying that you have a piece of soil here that has high resistivity. Well, it would give you a signal as you went over it. And so you'd be able to, if you're designing a road and you wanted to know what the material was that the road cut was going to go through, or if it's a landfill and you want to do a traverse, maybe you'd be able to pick out the corner of the landfill. Because the leachate inside the landfill might have high conductivity, and so in that particular case you might measure very low resistivity, high conductivity, reciprocally low resistivity, and this would give you an indication where the corner of the landfill was. So that's one way to use it. The other way to use it is in sounding. And so the idea then is that you take this arrangement, you measure the resistance in the center of this, and because the lines spread out to some size that's dependent on where the separation of these inflow and outflow points are, it kind of measures the resistivity in this zone best. If you expand the electrodes out to a greater separation, then it starts to average a bigger area. If you take it even further, it averages an even bigger area. And so physically what it's doing is it's not only averaging a bigger volume in the subsurface, but it's also averaging a deeper penetration, right? So it's giving you information as you get further, deeper and deeper. And so this sounding is kind of the same idea, but instead of keeping the template the same separation and physically moving it across the surface, you just expand it in one location to be able to do it. And so what you do is you get some average value of the resistivity in this region, which is a function of the separation of these electrodes. And so if you plot that resistivity as a function of the separation of the electrodes, you get 1 point. If you make the separation larger, you move down this axis, you get a different resistivity. And so you end up with a profile like this, and it turns out that you can then invert this profile to find out exactly what the change in resistivity is as you go down through this material. And so by measuring the apparent resistivity, which includes kind of the geometry of this, you're able to make a picture of exactly what's going on. And so, yeah, and so that's really the two modalities in which it's used. Profiling to run a traverse, and sounding to be able to look at variable depths. We don't need to worry about the fact that Ohm's law actually is very similar to either Fick's law or Darcy's law, but it just measures the electrons that are driven through a system given by a potential gradient in electrical voltage, as opposed to flow of water that's driven through a system as driven by a pressure, a head gradient. But the ways in which these arrangements of the inlet electrodes, if you like, the power electrodes on the outside and the measurement electrodes on the inside are arranged, give you a variety of different profiling methods. And so the Schlumberger brothers, as they then were, this is where they got their start. Before Schlumberger became the big oil field company, they were geophysicists and working on electrical resistivity methods. So the Schlumberger method has a certain arrangement of electrodes where the distances between the measurement electrodes and the injecting energy into the ground electrodes are arranged in some particular arrangement. And when you convert the voltage, the voltage that you read versus the current that goes into the ground, right? So at every separation, you'll measure the voltage between these 2 points, M and N, and you'll measure the current that you're putting into the ground, two measurements that you can make. If you know what this correction factor is, which is a function of the geometry of these electrodes, you can measure what this apparent resistivity is. If you know what this apparent resistivity is, then you can plot this apparent resistivity as a function of the spacing L over 2. That's it. Nothing more than that. And the rest is theory. And the idea is that if you have a type curve, which looks like this, you can fit that type curve, that actual curve that you get, with type curves that are available, and it will give you a picture of what the subsurface looks like. And so an example of that is here. This is the resistivity on this axis, measured in ohm meters. So this is what you get from this scaling coefficient, the voltage that you measured between the central electrodes and the current that you know you put in from your batteries on the external electrodes. So this is exactly what this is. So that's what this point here is. And this is the distance, the separation between these two outer electrodes. Put the energy. That gives you 1 point. If you make it wider, then you get a second point. And then what you do with this curve is you just match it to type curves, or that's what you used to do. Now you just get a computer program to invert the data to see what the geometry of the subsurface would be in terms of, in the upper surface here, a certain resistivity material, below it material with a different resistivity, below it material with an even different resistivity, and you use that information if you know what the resistivities of different materials are. I guess low resistivities for clays, higher resistivities for granular materials. So high resistivities would be low conductivities. So I suppose you'd expect high conductivities for things like leachate in landfills. Do they have anything like that? I'm looking for this. No. Domestic garbage. Well, interesting things to have resistivity magnitudes that you have to go and measure. Obviously, they're measured by someone. Scrap metal, a low resistivity, a high conductivity, the reciprocal magnitudes, as you'd expect. So metal would have a low resistivity compared to other stuff. And sand, I guess, has a high resistivity. I guess that's right. If you look at overhead cables, you could imagine that quartz is actually a good insulator, and so it's actually, that's what sand is, basically quartz. And so if you know what the values of these are, then you can try, if you know what the measurements of these are, you can try and fit some material. Waste, clays, or whatever. So similar. So profiling is one method, and I guess we don't say so much about mapping. But mapping is the same idea. It's just that every time that you set your array down, you're really measuring the same area close to the surface, and so the difference as you go across here is really just sampling a given depth, down to given depth. So you could use it, as we said, to pick up a landfill edge if you profile it. You could imagine using it to pick up scrap metal in the ground. You could imagine that if your plume has some electrical properties such as salts dissolved in it, you'd be able to pick this up as well, because salt water would have a different resistivity from regular water. Yeah. So the problem, of course, is that if you have one of these profiles that you've measured as a function of resistivity, apparent resistivity versus separation between the electrodes. And of course this axis here, this length axis for the separation between the electrodes, you can think of really as just a depth profile, increasing depth as you have greater separation. Then the problem is that you can fit this profile with some misfit, I suppose, with a whole bunch of different models. And so they're ambiguous. And so you could fit this maybe equally well to a subsurface that looks like this, with different resistivities in it and different boundaries, to a subsurface that looks like this. And of course only one of them could be right, and so you have to choose between them. And so the other point I suppose that's worthwhile making is that the way to choose between them is that you have a drill hole close to a part of your profiling, and you use that drill hole to be able to figure out exactly which one of these you should choose between, because you know exactly what's there. You know what the real material is. And so that's the method in which you could use it. Okay. And you could also do these, maybe we'll look at some pictures today. You could imagine doing these resistivity profiles, not necessarily in making them wider to look more deeply, not necessarily taking a template and moving it horizontally, but you could imagine setting it up so that these electrodes between the juice that you put into the ground on the outside and the measurements you take of the electrical drop across these two are, instead of changing lengths and separations, you change azimuth. And you do use this, can use this. For instance, if you have fractures, which might be water-filled, then as you change azimuth of these measurements for resistivity, then if you're arranged along the azimuth of one of these fractures, you might be able to pick up the fact that you'd have fractures of that orientation at that particular point. And so you can use it to actually to look at the azimuthal arrangement of fractures in the subsurface. So that's one application of it. The other way to do it, or another way to do it, is to use it in tomography. And so the idea in tomography, I guess there probably is a picture here. Yeah, I guess a good enough picture. And so this is a site which has been pegged for remediation. So it's got DNAPLs filled in. You can't really see much from the surface. But what it is a fractured rock site. And I think what they've tried to do here is to put in the subsurface, probably the central borehole here, either do thermal remediation by injecting hot steam or hot water, or put a heater in the ground, with the idea that any stuff that's present in place, if you heat it up, it will evaporate and vaporize. You cap it so you can catch it, and in catching it, then you've basically taken it out of the subsurface and you've removed it. And so what you might be interested in doing is knowing how well this is going, as to how much you might have taken out. And so one way to do that is to do what's referred to as electrical resistance tomography. And so the idea is that you have two other boreholes on either side, or actually four, I guess, in this particular arrangement. Imagine this is one, imagine this is one, this is one, and this is one. Think this is a heater hole. And what you could do is you could arrange to shoot from here to measure the electrical resistance between these 2 points on a ray path, just as you'd have tomography done of your head. Tomography of your head has a radioactive source. It shoots from this side. There's a detector at the other side. It measures how much that source attenuates as it goes across your head, and then it does that from a whole bunch of different angles to be able to look at those ray path velocities or attenuations and integrate them in some way to be able to figure out how at every single point in your head it's being attenuated by a velocity of that piece of your skull or your brain. And once it's solved that, it has a map of the whole inside of your head. And so this is doing the same way. It's shooting across here, but it's going to identify every single point really only within this plane, right? Because it can only shoot along this plane. Everywhere along this plane, which you can't see very well here, it would figure out a little contour map of what the electrical resistivity or conductivity would be by shooting from a source here across here to all of these sensors. So maybe you'd have 10 sensors in this hole, 10 sensors in this hole to be able to get this conductivity map. And as you look at the conductivity in time lapse, you look at it day 1, day 5, day 20, day 100. If it's changing and you have a relationship between the resistivity of DNAPL in the ground and resistivity of the ground without DNAPL in it, then you can actually plot how it gets remediated as a function of time. And so it's not a very good plot here, but that's exactly what's going on from days, I guess the 13th of June, the 23rd of June, 27th of June, etc., till October. So over, no, this is July, right? So the month, so over 2 months. So it can be used as some kind of remediation method. And you have some details about it at Edwards Air Force Base is California, Southern California, right? Where the space shuttle used to land. Okay. So we said we're talking about geoelectric methods, and I skipped over this quickly. But geoelectric methods come in a variety of flavors. The ones that we've talked about so far are direct current methods. So a battery in a car is direct current. Battery in your computer or your phone is direct current. And it gives you a straight voltage drop. The other way you can do it is you can use either alternating current, or you can use alternating current to create a magnetic field. And a magnetic field is due to changes in the voltage, alternating voltage. And so here you're measuring the transmission of electrons in the subsurface. Electrons travel at the speed of the light in the subsurface, but what you're measuring is the characteristic of the subsurface in terms of its electrical resistivity. In electromagnetic methods, typically, of which GPR is one, is you're measuring the speed of that electromagnetic wave, which is basically the speed of light. And other AC electric methods, which are not so widely used. So we will talk about GPR, but the other thing you could imagine doing is putting some current into the ground in some way and turning it on, letting the ground come to some steady state, and then you turn it off. And you can imagine if you turn the current on, leave it on for some time, and turn it off, then what you might do if you measured the secondary induced potential somewhere else is that you'd measure that ramping up to some magnitude, and while it's still turned on, it would reach some steady state, and as soon as you turn it off at this one coil, then it actually decays in the subsurface. And if you measure that decay, maybe you can say something about the subsurface. So this one form of electromagnetic waves are that you have a big coil which you place on the ground, which is your transmitter. You turn it on, and it lets it change the ground in some way. And with another coil somewhere else, you measure how the ground underneath this receiver changes as you turn it on, and also as it decays as you turn it off. So this is the transmitter coil, and its time sequence. This is time along here. And this is the secondary coil, is measuring the response. And so the idea basically is that you can measure the rate at which this decay occurs, and you can say something about the characteristics of the subsurface. The reality is that for environmental geophysics it's almost never used. Where it's used often is used if you're looking for ore bodies that are metallic, and therefore there's some secondary field that gets set up around this metallic ore body, the iron in it, I suppose, and you sense it from that. And so it uses electromagnetics in that way. Actually, I think it's the way that it's typically a very low frequency electromagnetic wave, and it's actually the wave I think that submarines communicate. And so very high frequencies, if you scream at someone versus if you talk in a very deep voice, the deep voice will project much further because it won't get attenuated so easily. So electromagnetic waves are the same way. So if you want to send a signal from a submarine in the middle of the Pacific Ocean to somewhere else, you use low frequency electromagnetic waves, very VLF, to be able to communicate. And so, yeah, I guess that's just an aside rather than anything else. So almost never used in environmental geophysics. But quite heavily used are ground penetrating radar. And so there are three more methods we'll talk about. One is using GPR, one is using seismics, and the other one is using gravity. So gravity is almost never used. If you want to find North Koreans digging tunnels into South Korea, you can use gravity for that. It picks up if you've got a void underneath you. But the ones that are quite broadly used in environmental geophysics are ground penetrating radar and seismics. They both work on similar principles. They both measure the speed of radiation in the subsurface. Radar is electromagnetic radiation, and seismics is acoustic radiation, speed of sound in the subsurface, and work in the same kind of modalities. So the idea for GPR, just as in the same way as you track an airplane, you send out a signal, signal goes out, it hits the airplane, bounces back to a receiver. Typically the receiver is in the same place if it's a radar station, but in GPR they're typically separated by a small length. And so if you measure the amount of time it takes to go from transmission to the object and back, the two-way travel time, then you can say something about the distance of this object if you know what the velocity is of that wave. If you have a plane that's further away, it'll take longer to come back because the two-way travel time has to go further, and therefore if you know the velocities you can reduce it for that. So that's the way it works. So typically what you'd get is a profile. So you'd pull these two things which are linked together, and you'd physically pull them across the surface of the Earth, and so you get a profile as you move from location to location with some baseline separation. And as you pull them from one location to another, to another, to another, what you'd end up with is a record of these pulses giving you the travel time, the two-way travel time, maybe to this top reflector, and then maybe to this bottom reflector, as you end up getting this continuous profile as you go across here. And so you'd end up with a profile that would have a two-way travel time to each of these features, these reflectors, which aren't acoustic reflectors, but they're reflecting a radar wave, which is traveling at close to the speed of sound. And so, yeah, so the easiest way to look at this would be a reflection that would look like this. And so this is actually a reflection from running the probe across the surface of the ground. Actually, it's a surface of river ice in this particular case. So it's a frozen surface of the Mackenzie River. Each of these little features is the travel time taken to go from the pulse to come down here and bounce back to the surface. And so you see some reflectors here, which represent some kind of interface. You see some kind of reflector here. You have to interpret it in some way. And you see, maybe with the eye of faith, a reflector here. You have a drill hole that goes through here. And that drill hole, if the legend, I don't think, oh, the legend is here. Perhaps you can't see the legend so well. I'm pretty sure that the drill hole is ice, river ice at this point. Water in this length. I think sand on the bed of the river. And I think this is permafrost right here. That came out of the borehole. And so now you have a way, if you have a signal that goes across here, and I don't know what it does over here, but you've mapped this out, is you know that this is, oh no, this is clay, I guess. Yeah, okay, no permafrost. This is sand, this is clay. So all of a sudden you have the clay-sand interface that goes off somewhere, You have the riverbed interface that goes off somewhere and does this. You have the ice, which should be roughly constant thickness, you'd think, as it goes across here. And now, if you know what the two-way travel times are, and if you know what the velocities are of each of these materials, roughly, for ice, there's ice on here, I don't see ice on here. But if you have it for water and air, you can use these velocities. Actually, you see they don't vary by very much, right? They vary. Not fat clay is expansive clay. So 0.13 to 3 is a factor of 2, which isn't so much. And so you'd be off by a factor of 2. If you choose some electromagnetic wave velocity, you can reduce this to actually get a depth of these components. So that's basically the method by which electromagnetics work. So the fact that it bounces off other materials is controlled by the dielectric constant. And so if the dielectric constants are the same and they don't contrast with each other above and below, you get no reflection. And so there is no contrast. So the material property that allows them to bounce across each other is this dielectric constant. Typically you can use multiple antennae at different frequencies, because different frequencies penetrate to different depths. Lower frequencies would penetrate deeper and give better. So it's this interplay between deeper penetration but poorer resolution, I guess, would be what you'd be looking at. And so those would be what ground penetrating radar would be. Seismic methods are pretty much the same idea, except now it's acoustic velocities you're measuring, which are much slower, not the speed of light, but maybe 600 miles an hour in air, 1,000 kilometers an hour, I guess, something like that, and higher velocities in rocks. They work in two modalities. It used to be that only oil field surveys were done in reflection mode, in which case you do exactly the same. You have a shot, which is sometimes an explosion, hits a reflector, comes back to a geophone. You'll have a whole series of these geophones on the surface, and this reflected wave will measure the two-way travel time in going down and up. If your reservoir is 10 kilometers deep, and the separation of your geophones on the surface is a kilometer, then it's almost vertically up and down the same travel path. If you're doing environmental geophysics, where the layers you're interested in are maybe 10 or 100 meters deep at the most, then 100 meter spacing on your geophones is no longer direct reflections. And so just the geometries of how you might do it in environmental geophysics is that you can use either reflection geophysics, which is basically what this is, just like radar, no different, where you get the reflected wave, or you can use seismic refraction, where the idea is that you put some energy into the ground here. This has a wave velocity on the surface and a wave velocity below it, which is different. Typically, as you go deeper in the ground, the rocks are more compact and denser, and therefore the velocity on the lower stratum would be greater than the upper one. So in other words, the pulse in going from this point to the geophone on the surface, where it will start shaking it, can either go this way, the shortest path, but through the slowest medium, which might give you a first arrival, or it can go through the slow material into fast material and go in that fast material for a certain length and then kick back up through the slow material. And so clearly when you're very close to this, it's much faster to go through the slow material on the surface, and you'll get there first. And that will be the first arrival. But as you get further away, it may be faster, instead of going directly in this direction, to go down here through the slow material really quickly across here and then back up. And so the idea is that as you get further away from here, you'll start registering the refracted wave, which has gone down here, has refracted along this surface, and gets back at the first arrival to this point. And so if you plot, for instance, the distance from the geophone on this bottom axis, and you plot the time that it takes for that first arrival to come, then the traveling on the surface would give you these arrivals here, all the way on this line, right? As you increase the distance it travels, it should be a straight line. So this will be the time traveled for a given distance. This will be the velocity of this, right? Because velocity is just equal to length traveled divided by the time taken. So this is just this. But at some cases, you get further away from here, it's faster to go down here, along here, and up here, and you'll arrive before this line. And so at this point, the refracted wave, it'll start off slower in the early point. So certainly the refracted wave takes a long time to go down here, really quick, a long time to go back up here. So this wave will have traveled shorter and arrived here first, but the refracted wave will be a later arrival. So this line here is the path of the refracted wave. And so you can imagine that if these are the data you plot, if you just plot the first arrivals, this would be a first arrival, this would be a first arrival, this would be a first arrival, this would be a first arrival. And so if you draw this line and this line, you get a nick point. And this nick point allows you to say where it's changing from, the short-circuiting wave arrives first, and this path allows you to define a critical time, or critical distance, sorry, and a critical time. And this allows you to say something about how deep this layer is. And so if you do this on a real section, explosion here, measure the travel times, and you get one curve. The same geophones, explosion here, you get a curve here, and a curve here of just the time for the first arrival to occur versus how far you are away from the shot points. If you take all of these curves and you make them into straight segments, then all of a sudden you have these nick points which give you a time when this turnover occurs and a time when this turnover occurs. So in other words, sorry. I know I'm getting a bit scrappy here. So you have a straight line segment here, you have a straight line segment here, and a straight line segment here. So it's just like three versions of this. So from these lengths that you have, so the times that you have for these first arrivals, and the lengths at which they occur away from the shot point, you can interpret this into a section which has, in this case, three layers. Top layer, second layer, third layer. And actually there must be a fourth layer here. So here this is saying, no, that's right. First layer has a certain seismic velocity and has a certain depth. Second layer has a different, larger seismic velocity and is deeper. And the third layer below that has an even larger one. And so now you have enough information to say how deep these layers are. You have something to say how fast they are from the slope of this line. And you also have something to say if you know that a certain kind of rock has this certain velocity, then you can correlate what that material is. Or you can have a borehole that goes down through here that allows it to sample directly to say exactly what these materials are. So those are seismic prospecting methods. So remember, they come in two varieties. They come in seismic reflection, which used to be the domain of the petroleum field because you're sampling down maybe 10 kilometers. The lines might go tens of kilometers on the surface actually as well. So when you fly across northern US and northern Canada and see these long lines which have been carved out of the forest, those are often cut lines that are have been used for exploration, sometimes. And so it was not typically used in seismic reflection for environmental methods because the equipment wasn't good enough to get the very short travel times that you'd have, but now it is. So seismic reflection is used in environmental geophysics, but also more used is seismic refraction, which is the second method. Both of them allow you to say something about how deep the layers are and what their seismic velocities are, acoustic velocities are, and from that to compare that with models for a seismic velocity for a given rock to be able to figure out exactly what's in place. And so you see some other pictures of what it is here. Gravity methods, I think, are exotic, not used so much in environmental geophysics, primarily because you're not often looking for caves, and that's really what they pick up. And the basic idea is that you can imagine that if you had a really dense, if this room was filled with lead instead of you, and you measured the gravity next to it, because lead is much denser than the air and the earth around us, it would measure an increase in local gravitational constant, 9.81 meters per second squared, next door to it. Likewise, if instead of having lead, you cut a hole out of the subsurface, so the density of this was the density of air rather than material around it, if you measured the attraction of a weight to the Earth as you go across this section, you'd find that it's less attracted to the Earth here because there's a mass deficit. And you can use Newton's law of gravity to define that. Newton's law of gravity says why the moon is attracted to the Earth and goes around it, is held where it is, and likewise says why, if you measure the attraction of a weight in a measurement instrument, it's attracted to the Earth, but also the Earth with a small amount removed from it. And so if you can measure the gravitational field very accurately, you can pick up the location and the size of different things in the subsurface. The negative, unfortunately, is that all the corrections that you have to apply to be able to correct for the fact that you are in different locations on the globe and therefore has different gravitational attraction, how high you are relative to the center of the Earth, whether you're sitting in Kansas or in the bottom of an incised valley or on the top of Denali, for the fact that there are earth tides that go on, all of these corrections have to be applied to the measurement. And these corrections are often of the same order as the discrepancy, the deviation from the norm of the measurement itself. And so it's really, it works, but it's actually kind of fraught with problems. So maybe we should stop talking about that there. So these are all the methods that can be used for profiling. And so let's look at some pictures and see if we can look at this. So these are a bit hokey, some of these figures. Let's see, can I do it at full screen? I don't know if these will get bigger. This is, or was, in 1982, a 12-channel seismograph. These little things with the knobs on them are just amplifiers, and the knobs are gain. This little flap here comes up so you can look down into it. And into it goes a cord which is attached to 12 geophones, which typically look a bit like this. So these little, whoops, oh, that's interesting. So these little conical things are physically pushed into the ground. All it is a magnet that sits inside a cage. And when the pot moves by the first arrival, the cage, the magnet in the middle, by its inertia, tends to stay still while the cage rotates around it or jiggles around it. And as it jiggles around it by Maxwell principle, right? A magnet moving in a magnetic field creates a current, and that current is just the pulse that's recorded and sent back to the seismograph. They're pretty mobile. So these are the cables that are used. These are a reel of cable. They will take the cable out over a couple of 100 meters. That actually has connections where you just attach these individual geophones, maybe at 30-meter intervals along the length of the cable, once you put it out. You have all that fed into this seismograph, which is recording it, with your jacket there so that you can put it over your head and so that you don't have the sunlight disturb you. And you use a quarter stick of dynamite to either put in the ground or to put in the water and trigger with a blasting cap to give the seismic impulse, which is the motivation that you'll read. So you trigger it, you know the exact time that it's triggered because you've given it the electrical pulse, and then you measure the first arrivals of the seismic waves as they arrive at the instrument. These we've all seen before. These are actually on the website, actually, if you ever want to go to these. I think we've seen all of these. Didn't see these. This is in Pennsylvania, a rotary rig, in this case drilling with air, drilling with a very big rotary bit, probably 14 inches in diameter, to get through the surface to the rock top and then put casing in, and then a hammer drill. And so this is the same rotary drill, but instead of tricones, it has, you can see that it's kind of disconnected here. So you can imagine maybe that this left-hand bit is moving in and out, up and down on a central spindle inside this. So all that happens is you power high-pressure air or water or drilling mud down here, and as it comes out of here, it drives this like a jackhammer. So there's a little valve that makes this end drive like a jackhammer. It has these little button pits on the end which bang against the end of the borehole. And as it bangs against the end of the borehole, it breaks little pieces off. The fluid comes out of the bottom and washes back up the side and physically takes it up to the top of the borehole. And so it rotates slightly as it does it, so it gets a new face with each of these button cutters as it goes down. And the size of this is probably 8 inches in diameter. And the rest are this drill well casing that is suspended in the hole. This is just the casing that goes down to rock, which is about a foot in diameter. And this actually goes 300 feet down into an abandoned underground mine near New Florence in Pennsylvania, where the project was to actually backfill this mine with fly ash to look at what happens. The idea that fly ash you don't want to have, it's a pain because you burn coal, you end up with fly ash, you have this big surplus which you can't use as a byproduct. You have acid mine drainage, and so maybe you can put fly ash into the ground to do two things. You can stop the drainage by filling up the mine voids so there's not so much water going through them. You can also fill it up so it takes care of the air because it's now saturated and you won't get the reactions that cause it. But then the worry is that because fly ash is the product of burning coal, which basically takes all of the heavy metals which are present in that large mass of coal and concentrates them in this residue, you're worried that if you have acid in the fly ash, you leach out these heavy metals and you don't help things downstream. And so that was the project. This is a borehole camera. I don't know if I've got a better picture of it. Being lowered down a tripod on top of this same borehole. And it's not quite like the cameras you might hold in your hand, but in this there's an illuminated light, an LED, and the camera lens may be an inch in diameter, and it's lowered down on an armored cable, and it looks at the side of the borehole and is able to rotate itself around to look 360 degrees at the borehole wall. And this again, this is New Florence. This is an air gun giving a seismic shot in a borehole. Happens to be in near Vichy in France at a geothermal project. Down this well with a tripod on top of it. Toronto, I think we saw this. These are drilling wells. Actually, you can see it much better there. I think this is the lens and this is the light. And actually, this one is actually a mine rescue borehole camera. So not used so much to look at the wall, which you'd expect that the light and the lens would be close together because there's not much separation between the camera and the borehole wall. But this one is arranged to be able to look out into a mine void once you drop it down into the mine void through a borehole, if you're looking for people who might be trapped. And the separation between the light and the lens is much larger. A downhole well, and a bunch of other stuff. So I did say that we're talking about geophysics. So this is the reason that I had that other thing open in the browser. Was there a different? I thought I had a second one. I thought I had. So this is a curiosity. This is the town of Plymouth in Montserrat in the Caribbean in 1995 when the volcano behind it started erupting. And I'm now looking at this, and this is 7 years later in 2002 where it's not actually airborne ash. This is the erupting volcano. It's just ash that's been accumulated closer to here and has actually washed out this town of maybe 7,000 people and just inundated with reworked waterborne deposits. It's not ashfall. It's not a catastrophic cloud that's inundated it. It's just slowly started burying it by being remobilized. And so it's only a curiosity because these are some of the few photos I have of other geophysical methods. So we talked about radar. And GPR, I think that's exactly what these are. So this is a radar transmitter and receiver. So they're just moved along this line to be able to move them closer and closer to each other. Again, part of this. This is a geophone, physically stuck a spike into the ground, probably a one-component geophone. It just measures when it starts to vibrate, not measuring whether the direction is horizontally in the two directions or vertically. It's attached onto this overall cable just by clipping it onto this cable. So this cable will run a couple of 100 meters and will take maybe a dozen of these geophones. And in this case, rather than using a half stick of dynamite, the other thing you can do is you can hit the ground with a very heavy sledgehammer. And so you'll see on here that there's electrical wire attached. The plate is metal, and so the electrical plate is also set up to complete a circuit. So that when you bang the plate and put the energy into the ground, that records the exact time just by physically completing the circuit. You know when the first impulse was made, and so if you measure the arrival times in the other geophones, one of which looks like it's right here, you can you can get these time distance plots. All of the cables put out here to be able to attach to the geophones. This is Chuck Amon, actually, if some of you know Chuck. He's a professor in geophysics here. Setting stuff up. Yeah, okay. I wasn't here, but I'm pretty sure these are radar transmitters, measuring a defined separation between them. Or it could, yeah, no, it must be. Yeah, it must be. And I think that this is an electrical resistivity survey. A battery, cables that go out to energy into the ground, measure the voltage difference between two electrodes between them, change the configuration of the electrodes, and you get one reading from a voltmeter to tell you what the resistivity is at these intermediate positions. Jürgen Neuberg from the University of Leeds. Don't know what that is. I don't think these. And this is on a different island. This is on the island of Martinique. So the island of Martinique in 1902 suffered a volcano collapse, a big nuée ardente, a glowing cloud. It's a French translation of a nuée ardente. I guess probably the terminology came from this eruption. Came down on the town of Saint-Pierre and killed 28,000 people. It's an ash cloud that travels at the speed of a hurricane. It's full of ash and hot gases from the lava dome that's collapsed, and comes down at 200 miles an hour, and is maybe 500 degrees centigrade. Just wiped the city off the face of the earth. The one person that survived was a guy called Cyprius, I think his name was, And the reason he survived was he was in jail for being drunk. And this is his jail. And so that's why he survived, because he was in this nice cold cellar, which kept him away from the perils of the devastation from Montpellier and the town of Saint-Pierre. I think that's all I've got. So, geophysics. So we've said that one of the techniques, one of the reasons for geophysics is to be able to measure behavior on the surface and to correlate that with what goes on in a borehole. So the other form of geophysics, as opposed to surface geophysics, is borehole geophysics. And I think it's not so widely used in environmental applications, but is widely used in the oil industry, where your wells might be 10,000 feet, 20,000 feet deep. You don't have samples, and you'd like to know what the stratigraphy is as you go along it. So what you could use is you could take a sonde like these, and you drop it down it, and you record some parameters as it goes down, and then you pull it back up and you record the same parameter, and you use that parameter to say something about what's in the subsurface. And so these geophysical signals are measurements of the natural radiation, the gamma ray count, which is used to tell you whether you have clays in the formation. It might measure the width of the borehole with a bowstring caliper log, or with a caliper like this, which measures how wide the borehole is, which might tell you areas where the borehole's collapsed. There might be things like silts that are unstable. It might measure the electrical resistivity along the borehole in exactly the same way as a Schlumberger probe measures it on the ground. You put energy into the wall at one place, and you have a voltmeter that measures the difference in volts at another location. It might have a little impeller that measures the flow velocity in the borehole as you drop the probe down, and then as you pull it back up. If you subtract the two measurements of the velocity of that impeller, you can see whether water is flowing into the borehole at some place and then flowing out at some place, because there'll be a signal in there. It's exactly the example we use to talk about substantial derivatives, moving frames of references in 303. And it might measure neutron backscattering to measure moisture contents. So a whole bunch of signals that we can use, which I've kind of gamma ray. You can measure densities, you can measure water contents, you can measure electrical resistivities, you can measure the salinity of the formation, really by measuring electrical resistivities. You can measure temperatures, seismic velocities, the diameter of the borehole, flow in the borehole, and how it deviates from the vertical. And you basically drop a probe along the length of it, and you get a trace, and you use multiple measurements of these, which have different attributes, to be able to decide whether it's shale or sandstone or weathered shale or clays, etc. And to be able to reduce the data to be able to figure out exactly what it might be. And so, as I say, not used so much in the groundwater arena, but certainly used in petroleum. And finally, I know you're chomping at the bit to get out of here, but finally, if you want to ever use these methods, there are two tables, I think, at the end of this, I guess one table, that says something about the applicability of these. And so we've talked about seismic measurements, we've talked about gravity measurements, magnetic measurements, electrical resistivity measurements, radar, and borehole logging. And this gives some idea of whether they're useful in different things. Whether you'd want to use seismic to pick out leachate plumes. No, you don't want to, because there is no signal it picks up. Seismic doesn't say anything about the electrical resistivity, which is probably really the only signal you have in a leachate plume, because you have lots of salt in it. But electrical methods may do, and radar probably doesn't very much. And so you can figure out exactly what you might use if you're ever in the position to be able to commission one of these survey methods to be able to apply at a place where you might be working. So I'll leave it there. Thank you. So